Hello everyone, my name is Zuwei Lo, and today I'm honored to present our research titled The Application of Image Recognition and Model Distillation in Monitoring Pedestrian Priority Violations. In this work, we explore how deep learning and knowledge distillation can be effectively applied to enhance real-time pedestrian detection in smart traffic enforcement, especially in complex urban environments like those in Taiwan. This presentation will walk you through our motivation, methodology, experimental setup, and key findings. Thank you for your attention. In early 2023, Taiwan experienced a sharp increase in pedestrian priority violations, with over 13,000 cases recorded in just 2 months. That's a 71% jump compared to the same period the year before. By the end of 2023, according to the National Police Agency, the total number of violations had exceeded 139,000. This includes more than 57,000 from cars and over 81,000 from scooters. While some of this rise may reflect stricter law enforcement, it also shows that many drivers are still unclear about when and how to yield the pedestrians. As you can see in the bar chart, car-related violations surged by 191%, and scooter-related ones by 162%. On the right, we show the real-world images taken in late 2024. These highlight common safety issues, like failure to yield at crosswalks or blind spot during vehicle turns. All of these point out an urgent need for an AI system that can detect pedestrian risks in real time, issue early warnings, and help ensure fair and consistent law enforcement. In this section, we define the core challenges and objectives for our research. First, while lightweight models like YOLO version 8 Nano are fast, they often struggle in complex urban environments. This includes situations with occlusion, poor lighting, or busy backgrounds, all of which are common in real-world traffic scenes. Second, real-time applications demand fast inference, which makes it hard to use larger, more accurate models due to their latency. So, our central research question becomes, how can we improve the robustness and recall of YOLO version 8 Nano without sacrificing its speed? To solve this, we introduce a knowledge distillation framework based on 3 strategies: response-based, relation-based, and feature-based distillation. Our goal is to transfer different forms of knowledge, including semantic, spatial, and relational calls, from stronger teacher models to YOLO version 8 Nano, so that it can perform better while remaining lightweight and real-time capable. On this slide, we introduce the concept of knowledge distillation, a technique that transfers useful information from a larger, more powerful teacher model to a smaller, faster student model. There are 3 main types of knowledge we can distill. First, response-based knowledge, which comes from the teacher's final outputs, like classifications, logics, or bounding box predictions. Second, feature-based knowledge, which is drawn from intermediate feature maps inside the model. Third, relation-based knowledge, which captures the internal structure between features, such as the relative distance or angles between them. Each type of knowledge represents a different level of model understanding. In our study, we propose 3 knowledge distillation strategies, each targeting a different level of model representation to improve YOLO version 8 Nano's performance, without sacrificing its real-time speed. Method A adopts a response-based approach. We use faster RCN as the teacher because of its high prediction accuracy. The students learn by aligning both the classification logics and bounding box outputs with those of the teacher. Method B focuses on relational knowledge. We choose Distinction Transformer as the teacher, since its transformer architecture captures global object relationships. We extract feature embeddings from both models and apply RKD losses based on relative distance and angles between features. Method C applies feature-based distillation. We select YOLO version 8 Large as the teacher because it shares the same architecture family as the students, making feature alignment more effective. We match intermediate feature maps using MSE laws. All 3 methods are trained on the COCO dataset, allowing us to systematically compare how different types of knowledge, response level, relational, and feature-based, affect student performance and robustness in detection tasks. On this slide, we show side-by-side comparison of the teacher and student model architectures, as well as the inference pipelines. The sandboxes highlight where each method extracts knowledge from their teacher. Method A focuses on logit, distilling information from the final output. Method B transfers relational features, capturing spatial relationships across layers. Method C allows convolutional feature maps from intermediate layers. This comparison illustrates how each approach taps into a different level of the model hierarchy, from output predictions to internal structures, to guide and improve the student model's performance. To start Method A, we preprocess and filter the COCO dataset to ensure compatibility between both models. The student then tries to replicate the teacher's final predictions, including bounding box coordinates and class confidence scores. We apply L1 loss to align bounding boxes and KL diagrams to match class distributions. These losses are computed after using IOU matching to pair corresponding predictions. The key advantage of this approach is that it doesn't require any changes to the student's architecture. Instead, it enhances performance by aligning outputs, keeping the model fast and lightweight. In Method B, we choose detection transformer because its transformer architecture captures global object relationships using attention mechanisms. This makes it ideal for transferring relational knowledge. The strategy focuses on spatial relationships between feature vectors, including relative distance and angles in the feature space. To bridge the gap between architectures, we extract intermediate features and use one-by-one convolution and reshaping to match the dimensions between detection transformer and YOLO version 8 nano. We then apply two relational losses, RKD distance loss, to preserve how far features end from one another, and RKD angle loss, to retain the geometric structure between feature triplets. Together, this helps the student model gain a deeper spatial understanding, enhancing detection robustness in real-world traffic scenes, without increasing inference time. In Method C, we apply feature-based distillation using YOLO version 8 large as the teacher and YOLO version 8 nano as the student. We choose YOLO version 8 large because it belongs to the same model family, which improves feature alignment and compatibility. We extract intermediate feature maps from both models and align them using one-by-one convolutions and spatial cropping. Then we apply MSE loss to help the student mimic the teacher's internal representations. This approach enhances spatial awareness and semantic understanding while keeping inference fast. In our experiments, we recorded 5 real-world videos using a Mel C580 dashcam, collecting a total of 9,000 frames. These samples were captured under diverse conditions, including daytime and nighttime scenes, rainy weather, and various traffic environments such as intersections and crosswalks across Taiwan. This diversity helps ensure the model learns to detect predictions reliably across a wide range of real-world situations. To evaluate the feasibility of real-time deployment, we also tested the model's inference speed on a Raspberry Pi 5, aiming to support lightweight and efficient applications in particle traffic monitoring. In the study, we focus on 4 key evaluation metrics: precision, recall, confidence score, and inference speed. Precision tells us how many of the predicted detections are actually correct, while recall reflects how many of the true predictions are successfully identified by the model. We also examine the confidence score, which ranges from 0 to 1, to understand how certain the model is about each detection. Analyzing its distribution helps us assess prediction consistency across varied scenes. Finally, inference speed measures the average time it takes to process a single frame. This is important for real-time applications like pedestrian monitoring in traffic videos. Together, these metrics provide a comprehensive understanding of both the model's accuracy and its practical usability. This table compares the models in terms of inference speed, precision, and recall. Starting from the top, Detection Transformer and YOLO version 8 Large deliver high precision but suffer from slow inference speed, making them less ideal for real-time deployment. Our baseline YOLO version 8 Nano is fast, but has low recall. Now look at the last 3 rows. These are our proposed distilled models, are using YOLO version 8 Nano as the student. All 3 methods maintain real-time speed, around 0.06 seconds. Among them, Method A achieves the best precision at 0.916 and improved recall at 0.409. Method B and Method C also show recall gains. We also report 3 standard deviations to reflect the model's consistency across all 5 samples. On this slide, we present the confidence score distributions across all models and distillation strategies. Each curve represents one of the 5 video samples, and the x-axis indicates the confidence level of predicted bounding boxes. We observe that the teacher models like faster RCNN and Detection Transformer show higher confidence peaks near 1, especially in clear scenes. In contrast, the baseline YOLO version 8 Nano and YOLO version 7 Tiny display more dispersed distributions, suggesting less certainty in their predictions. Notably, all 3 distillation methods, HIJ, result in smoother and more right-shift curves, indicating improved confidence and prediction consistency. This supports that knowledge distillation helps the student's model generalize better across varied traffic scenarios. We also present qualitative examples comparing baseline models and our free knowledge distillation strategies. We show a comparison of detection results for an occluding pedestrian in the crosswalk. All models except YOLO version 8 Nano were able to correctly detect the person. This highlights a key limitation of the baseline model, its difficulty in handling partial occlusion. In contrast, the distilled models effectively improve recall in such challenging scenarios. On this slide, we present 2 real-world misclassification examples. On the left, a pedestrian holding an umbrella is only partially detected. Some models miss the person entirely or detect only the umbrella. This shows how occlusion, especially from objects like umbrellas, can hinder detection in lightweight models. On the right, in a rainy nighttime scene, the model incorrectly labels the same region as both a motorcycle and a pedestrian, when it is actually a bicycle. This confusion often arises from reflections, overlapping shapes, or motion blur. These examples highlight a key trade-off. Improving recall can lead to more false positives, especially with partially occluded or visually smaller objects, like umbrellas, motorcycles, bicycles, and small traffic signs. To conclude, all 3 proposed distillation models successfully enhanced the recall rate of YOLO version 8 Nano, with Method A showing the most significant gain. However, we also observed a slight drop in precision, especially in Method B and C. This suggests a trade-off. Increasing recall can sometimes lead to more false positives. Interestingly, both the feature and relation-based methods proved effective at detecting pedestrians that were partially occluded, a common challenge in real-world traffic scenes. Among the 3, Method A provided the most balanced performance between precision and recall. Importantly, our distillation strategies preserved the real-time inference speed on YOLO version 8 Nano, making them suitable for deployment on edge devices. Overall, these results highlight the importance of choosing a distillation strategy that matches the complexity of scenes and accounts for common challenges like occlusion and low visibility. On this final slide, we present the key references that support our study, starting from Hinton's pioneering work on knowledge distillation. We also include recent research that applies distillation techniques to object detection tasks. Finally, we highlight the original sources of the models used in our experiments, including faster RCNN, YOLO version 8, and detection transformer. This concludes my presentation. I sincerely hope this research contributes to the partial deployment of AI in traffic safety and encourages further exploration in this important area. Thank you for your attention.